So we can perform a variety of operations on complex numbers in polar form. We can multiply them, we can take the reciprocal of a complex number in polar form, we can divide them. These are all things that we do with complex numbers when they're in rectangular form as well. Now, there are longer approaches as to how we can perform these operations. If you're interested, you're welcome to look through the examples in the textbook in the pages that precede the homework assignments. But we're going to focus on the shortcuts, the faster approaches that we can take to performing some of these operations. So, for example, if I have two complex numbers, z1 and z2, that are in that r kis theta format, instead of the longer approach that's shown in the book, the shortcut that we can take to multiplying those two complex numbers is to multiply the two r values of the respective numbers, multiply the moduli, the plural of modulus, and then we can just add the thetas, add the arguments. And so it's as easy as that to multiply two complex numbers in this polar form. So if I want to multiply z1 times z2, I'm just going to multiply the two r values. Sorry, I want to get that all the way to the 3. So 2 times 3. And then I'm going to have kis, the cosine I sine of 124 plus 27 is 151 degrees. So we just get 6 kis 151 degrees. And again, remember that this kis theta is cosine of theta plus I times the sine of whatever theta is. So it'd be 6 times cosine of 151 plus 6 times I sine of 151. And so that would be how we could convert it back to that rectangular form. And I should mention, if we did have our number, complex number in a plus bi form instead of in this complex form, in this trigonometric form or polar form, if I wanted to multiply two complex numbers, then I would have to use FOIL technique. I'd have the first one, a plus bi, times the second one, a plus bi, and then I would just multiply it that way. So I don't think FOIL is that difficult, but certainly just multiplying a couple r values and adding together the two angles is a pretty quick way to perform this multiplication. If we're trying to find the reciprocal of a complex number, so if I have some complex number and I want to find its reciprocal, you can see the approach there is I'm just going to take the reciprocal of whatever the r value is of the modulus and then just change the angle, the argument, to its opposite. So that just becomes negative. So if I wanted to find the reciprocal of this number z1, I'm going to take the reciprocal of r, so 2, take the reciprocal of that, I get 1/2, and then it's kis, or cosine of 124 plus I sine 24 becomes kis of negative 124. I just changed the angle to its opposite. And again, if we were working in rectangular form, in that a plus bi, if I want to find the reciprocal of that, well, I can't just throw it under 1 because I is a square root, so I have to rationalize that expression by multiplying by the conjugate pair. This is work that we did previously earlier in the year, so you can see that the mechanism for finding the reciprocal of one of these complex numbers when it's in this trigonometric form, it's a lot faster. Just find the reciprocal of the r value, change the angle to its opposite. If we're dividing complex numbers in this polar form, then it's going to be just the opposite of what we did for multiplication. So we're going to divide the two r values, and then we're going to subtract the angles. So divide the moduli, subtract the arguments. So in this case, if we want to divide z1 by z2, we're going to take 6 over 4 kis, and then 19 minus 96. So we can clean that up into 3/2 kis, And then 19 minus 96 is going to be negative 77 degrees. The last thing we have is something known as DeMoivre's theorem. And so this is when we're asked to raise a complex number in trigonometric form to some exponent, or to find the square root or a cube root, which is really also raising a number to an exponent. DeMoivre's theorem says that if we're raising our complex number to some exponent n, then the way we're going to do that is we're going to take our r value, the argument, and raise it to that exponent. And then we're going to take the angle and multiply it by whatever that n value is, by whatever that exponent is. Where this becomes a little bit tricky is in the case of when we're taking the root of some sort, a square root or a cube root of a complex number, like we're asked to do here. Because one of the things that we have to consider is that when we're writing it in a complex number in this trigonometric form, really we've got 8 kis 120, but because we have coterminal angles with 120, we really have a plus 360, maybe we'll call it k instead of n here, plus 360k, multiples of 360 that we have that are that we can add to that 120 that are coterminal. Because if we have our complex number here rotating some angle theta, if we add or subtract an extra revolution, we're going to end up at that same location. So there are infinite ways that we can represent a complex number in trigonometric form. We have to include this plus 360k as we apply this Demas theorem to make sure that we get the multiple roots. There's not just one cube root of this 8 kis 120 that we see here. There are going to be multiple roots. So let's see how that applies to this specific question here. So if we're raising, if we're trying to find the cube roots, so that means we're raising our number z to the 1/3 power. So we're going to take r to the 1/3 and then kis 1/3 of theta plus 360k, if we really include that plus 360k as part of it. So for this specific example, our r value is 8. So we're going to have 8 to the 1/3 power, and then kis, and then it's going to be 1/3, so that's our n theta. It's going to be 1/3 times 120 plus 360n. And so now if we continue with our simplifying here, the cube root of 8 is 2. Remember, it's not plus or minus because it's an odd root, so it's just 2. And then we've got this kis, and then we've got 1/3 is going to get distributed to that expression. So 1/3 times 120 is 40, plus 1/3 times 360 is 120n. And so what this means is now we've got, remember n represents integer values, we actually can find what are the 3 unique cube roots of this 8 kis 120 by plugging in 0, 1, 2 into our expression there. So the first of these cube roots is going to be 2 kis, and now I'm going to plug in 0 for n, so 2 kis 40. A second cube root of that number is 2 kis, and now I plug in 1 for n, so 40 plus 120 is 160 degrees. And then finally, if I plug in 2 for n, I get 2 kis, and then 40 plus 240 is 280 degrees. Now I could plug in 3 for n to get one more answer. If we did that, we'd have 2 kis. So now I'm up to adding 360. 120 times 3 is 360, plus 40 is 400. but 40 and 400 are coterminal with each other. So those two are the same exact location. So we end up not needing to list any more beyond those original three. And so in kind of a diagram format, so our first cube root of this 8 KISS 120 is going to be here at about 40 degrees with a length of 2 there for that red segment. 2 KISS 160, which is going to be right about here, and then 2 KISS 280, so that's going to be just past 270 right here. So there are 3 separate R KISS theta formats: 2 KISS 40, 2 KISS 160, 2 KISS 280, that if you were to raise those back to the third power, if you were to cube those numbers, each of those would get you back to this 8 KISS 120. And so what we find is whatever the root is that we're taking, if we're taking the cube root, we're going to end up with 3 separate roots. If we're taking a square root, we're going to end up with 2 unique roots. If we take the 5th root of a complex number in trigonometric form, we're going to end up with 5 unique roots. We don't have to worry about this plus 360k if we're raising a complex number to an exponent larger than 1. So if we're squaring it or raising it to the 3rd power, to the 4th power, we don't have to worry about this extra plus 360k. We can just use the n times whatever the angle is. And the reason for that is if I distribute a number like 2 or 3 to this set of parentheses, well, then I'm also going to be just adding multiple revolutions, so I'm just going to end up at the exact same location. So I know this is a little bit tricky to get across in kind of a video without being able to answer questions, so I really encourage you to look at the solutions to the homework problems as you go through them to see how this works in practice when we're raising a complex number to exponent larger than 1. You'll see this plus 360k just doesn't apply. It just disappears. But for these roots, the cube root, 4th root, 5th root, we're going to end up with these multiple answers, and we're going to have as many answers as we have the root that we're taking.